Hi, this is Arnav Varma. I'm pleased to present Dynamically Modular and Sparse General Continual Learning. This is a joint work with Elahir Arani and Bahram Zanuz. Continual learning refers to the learning protocol where tasks such as different classes arrive sequentially. This is in contrast with regular training where all tasks are available for training at all times. Examples where continual learning is of use include household robots, learning new skills, and self-driving cars, learning new traffic signals. Regular training strategies on continually streaming tasks leads to catastrophic forgetting of previously seen tasks. General Continual Learning, or GCL, is a realistic evaluation protocol for continual learning methods. The core condition to be satisfied for general continual learning is that the task to be performed or the task identity is unknown at test time. Additional conditions include maintaining a bounded memory footprint through training and having unclear or blurred task boundaries. An example can be seen in the image here. The different tasks or phases have mutually exclusive sets of classes in the upper half, which is a common continual learning protocol. However, in the bottom half, the tasks have overlapping classes, that is blurred boundaries, and therefore can be considered more realistic. Humans learn continually from inherently non-stationary data about the world without catastrophic forgetting. What's more, we do so without requiring supervision about arrival of new tasks or tasks to be performed and maintain bounded memory throughout. For our method, we have taken inspiration from two phenomena observed in humans when learning continually. First is dynamic, modular, and sparse response to stimuli. Humans show dynamic and sparse response to stimuli. This involves dynamically composing a subset of specialized neural modules available to respond to each stimulus. There are two advantages to this. 1. Relevant previously learned experience or stimulus can be reused for new experience or stimulus. 2. Information irrelevant to current stimulus but relevant for previously seen stimuli is not unnecessarily erased. To achieve dynamic, modular, and sparse responses, we use a network F, which has a policy to compose a subset of available modules to respond to stimuli. Specifically, we treat as modules convolutional filter or output channels which may or may not be activated for each stimulus. Every convolutional layer that can generate dynamic responses is embedded with an agent. In this diagram, we see the Lth convolutional layer of a network out of a total of capital L convolutional layers. The bottom part of this layer forms a reinforcement learning agent which removes the channels from the output activation based on the input to the convolutional layer. The agent first processes the input using a self-attention network. This involves pointwise convolutions to match the output channels, global average pooling to flatten to a channel length vector, and a single layer MLP with sigmoid activation. The output of this MLP is multiplied by its own input to get a channel-wise attention vector. A probability layer converts each dimension of each channel-wise attention vector to the probability of the corresponding channel being picked. We use a sigmoid with temperature as a probability layer. The temperature controls the range of probabilities and ensures that enough activations are picked each time. During training, Bernoulli sampling is used to pick binary actions based on these probabilities. During inference, actions are picked by thresholding the probabilities at 0.5. These binary actions are then multiplied with the output of the convolutional layer in the upper part to remove activations and get dynamic responses. Equation 1 shows the probability layer for the Lth agent and the Bernoulli sampling policy for the actions. Equation 2 shows the forward pass for classification for an input x, y, where the output v is a concatenation of channel attention vectors from all agents. Z is the logit and y hat is the predicted class. Equation 3 shows the reward function for each agent, where Kr or keep ratio refers to the target activation rate, whereas the sum of binary actions divided by the number of actions shows the achieved activation rate during forward pass. Therefore, when the DNN's predictions are correct, the agents are rewarded for dropping enough activations to match the keep ratio. However, when the predictions are incorrect, the agents are penalized for their actions, scaled by a constant penalty factor lambda. Note that the reward function for each agent is dependent on the correctness of prediction, which further enforces coordination between the agents. The loss for all agents with this reward function is calculated using policy gradients following the reinforce method here. This loss will ensure dynamic and sparse responses with the network composing different subsets of modules, that is channels, to respond to each stimulus. However, there is no explicit imposition of specialization on these modules being composed. In our case, the modules are along the channel-wise activations, which in turn depend on the channel-wise attention vectors V. Therefore, we apply a specialization loss on these vectors that we call a prototype loss. Specifically, in any batch of inputs, we pull pairs of vectors from the same class together while pushing pairs from different classes apart. Capital V is the concatenation of all channel-wise attention vectors for each input in the batch, and MSE refers to the mean squared error. This will cause different subsets of channel-wise modules to be used for different classes. Furthermore, if the keep ratio is higher than the inverse of number of classes, it will also encourage overlapping activations. For example, reusing channels corresponding to a learned class for a newly observed and similar class. Note that we only apply this loss to samples in the batch for which the predictions were correct. We now look at a second phenomenon observed in humans in the context of continual learning: multi-scale associations between current and previous experiences. This concerns consolidation of previous experiences and ensuring that past experiences evoke the same response. To this end, following other rehearsal-based methods for general continual learning, we use a memory buffer M of finite size that stores previously seen examples. The buffer is updated using reservoir sampling, which helps approximate the distribution of samples seen so far. Note that we only consider samples on which predictions were correct for addition to the buffer. The buffer stores the input, the label, the logits, and the concatenated channel-wise attention vector when they were first observed. At each training step, one batch each is sampled from the current task stream as well as the memory buffer. Now, to ensure that previous experiences, that is memory samples, evoke the same responses, a mean squared error loss is applied between current and saved responses, that is logits and channel-wise attention vectors. Altogether, there are 4 sets of losses in the total loss. Task losses, which in this case is cross entropy on both current as well as memory samples for learning as well as remembering the tasks. Reward losses based on policy gradients on current and memory samples for learning and remembering dynamic responses. Prototype losses on both current and memory samples for learning and remembering specialization of modules. Consistency losses on the memory samples for multi-scale associations between current and previous experiences, ensuring that previously seen stimuli evoke the same responses. Note that we use a warm-up stage at the beginning of training when no buffer or agents are used, which is equivalent to only using cross-entropy for training. This gives agents a better search space when they start searching for a solution. We call a method dynamic modularity and sparsity, or dynamos. In our experiments, we use a ResNet 18-based structure, but with 2 blocks instead of 4, and number of filters in the convolutional layers reduced from 64 to 32. Though we could use an agent for each convolutional layer, we only do so for the layers in the second block of a network. This is because of studies that have observed that earlier layers and their representations undergo minimal forgetting, are highly transferable, and are activated for more samples even when learned dynamically. We first look at results under the class incremental learning protocol, where mutually exclusive sets of classes are presented sequentially to the network. Task identity is not available at test time, and the protocol meets the core desiderata of GCL. To simulate the protocol, we use the sequential variants of SVHN and MNIST, with their 10 classes divided into 5 tasks containing 2 classes each. We compare against conditional convoluted gated network, or CCGN, which too composes convolutional filters dynamically for continual learning. We observe that Dynamos outperforms CCGN on both datasets for all buffer sizes. This is despite the fact that CCGN needs a separate task vector for each convolutional layer for every task, which can lead to unrestricted growth of network size. Dynamos, however, maintains a bounded memory during training. Additionally, CCGN needs the validation set and task boundaries during training, whereas Dynamos doesn't. Unlike in class incremental learning, real-world data streams without clear task boundaries and data may reappear under different distributions such as different poses. This forms the basis for the General Continual Learning or GCL evaluation protocol. Specifically, we use MNIST 360 dataset where tasks overlap in digits, that is classes, and reappear under different rotations, that is distributions. With this protocol, we study the impact of two aspects of a method: dynamic modularity and multi-scale association. Last row corresponds to naive gradient-based learning, where there is no strategy to counter forgetting. As seen in the table, this leads to catastrophic forgetting. First row corresponds to dynamos. The second row, with only multi-scale associations, corresponds to not using any agents and forms the baseline to show the impact of dynamic modularity. It can be seen that dynamos outperforms the baseline for all buffer sizes. We hypothesize that dynamic modularity helps in dealing with the blurred task boundaries by adaptively reusing relevant previously learned information, which here corresponds to learned filters. We will now look at some of the characteristics and advantages of a method. For these analyses, we evaluate the model trained on sequential MNIST with buffer size 500 on the complete validation set. We first look at the ability of dynamos to emulate modular and specialized responses. We plot the class-wise and task-wise activation rate for the last 40 dynamic convolutional filters for all examples. Figures A and B show a soft separation of activations with respect to tasks and classes. This is unlike standard networks where all filters will react to all examples. In figure A, we observe similar activations of similar classes, that is digits. For example, samples from digits 1 and 7 trigger similar responses, as do those from 6 and 8, and both of these pairs share similarities in shape. Dynamos can reuse and drop learned filters, which could explain response similarity indicative of input similarity. Note also that dissimilar digits do not lead to completely disparate activations, instead showing some level of overlap and therefore reuse. This could facilitate learning of sequences of tasks without expanding capacity or having a large capacity at initialization, which is a common strategy for continual learning. To quantify the overlap of representation between classes, we calculate the Jensen-Shannon divergences between activation rates of each class pair. Digit pair 1 and 7, which as we saw earlier have highly similar activation patterns, shows the highest overlap. Digit pair 1 and 8, where the digits are highly dissimilar in shape, has the lowest overlap. The correlation between representation overlap and class similarity is quantitatively observed. Now, as activation rates are controlled by the channel-wise attention vectors as seen earlier, we plot the t-SNEs of these vectors. Most of the samples for each class are clustered together. Moreover, clusters of visually similar classes are also close together. Take the digit 9 for example. It can be thought of as a line with a loop. It has two main clusters. One cluster is close to clusters of 6 and 1. 6 is very similar in shape to 9, and 1 can be thought of as a line, thereby sharing some similarity. Another cluster is close to that of 7 and 4, former of which is a line and latter is a line and loop. There are also examples that are scattered away from their class clusters, indicating that these particular examples are visually closer to examples from other classes. Finally, note that the similar examples and classes are spread across tasks. This explains the lower similarities between activation patterns of task pairs. So, to conclude, Dynamos learns modular and specialized units. The separation and overlap of activations or specialized units depends on the extent of similarity of the inputs. We also contend that the overlapping activations for digits of similar shape suggest the learning of general purpose features. Now, the brain is known to show variability in response across trials. For the same stimulus, the precise neuronal response could differ between trials, a behavior absent in most conventional neural networks. In dynamos, the trial-to-trial variability can be mimicked by using Bernoulli sampling instead of thresholding to pick the actions during inference. The figure shows the responses of the last 40 filters of the network for multiple forward passes on the same input. We only show responses if the prediction was correct. Every trial for the same input led to different activation patterns. However, there are also similarities across trials. There are some filters that are used in every trial and some that are dropped in every trial. So, to conclude, Dynamos outperforms dynamic baselines on multiple datasets under class incremental as well as general continual learning protocols. Dynamic modularity was also found to be particularly helpful for general continual learning. Dynamos also shows responses with similarities dependent on the similarity of the inputs, which could mean Dynamos learns general purpose features. Semantically similar classes led to overlap in activation patterns and the channel-wise attention vectors from which actions are picked. Additionally, dynamos can mimic the trial-to-trial variability seen in brains. We therefore consider a method as a step towards achieving modular general-purpose continual learning. Thank you.